Welcome to this explainer. Today, we're going to completely demystify Archimedes' principle. Now, we aren't just going to talk about abstract theory here. We're actually going to lock in your understanding through some concrete, step-by-step practice calculations. So by the end of this, you'll see exactly how the math perfectly lines up with the physical world around us. Let's get into it.
Here's our roadmap for today's explainer. We'll start with the weight loss mystery, move on to real versus apparent weight, solving for upthrust, Archimedes' Principle explained, calculating displaced fluid, and finish up with some rapid-fire practice problems.
Section 1, the weight loss mystery. Let's dive right in with a really fun physical puzzle.
Okay, picture this. Imagine you've got a heavy object suspended in the air by a spring balance. You look at the scale and it clearly reads 10 kilograms. Now, just to keep things super simple for our calculations today, we're going to use kilograms as our unit of force. So you've got a 10 kilogram force pulling straight down. But here's where the mystery actually starts. You take that exact same object, still hanging from the spring balance, and you lower it right into a tub of water. Suddenly, you check the reading, and it's dropped to 6 kilograms. Unless this object went on an instant magic diet, where exactly did those 4 kilograms go?
Section 2, real versus apparent weight. Well, to crack this case, we really need to get our vocabulary straight first. Let's split our observations into two distinct concepts. First, we have that 10 kilogram measurement of the object when it's just hanging out in the air. That original, unaltered measurement is what we call its real weight. Then, we have that reading of 6 kilograms, which we only get while the object is actively held underwater. That reduced reading, we call that its apparent weight. It's absolutely crucial to remember that the object's mass hasn't actually changed. If you pull the block right back out of the water, boom, the spring balance instantly goes back up to reading 10 kilograms. The 6 kilogram reading is purely apparent. It only exists as long as the object is held in the water. So the reason for that apparent weight drop is a specific phenomenon called upthrust, which you might also know as buoyant force. Upthrust is basically the upward force exerted by a fluid on an object that's immersed in it. When the object goes into the tub, the water is actually pushing back up against it. And hey, quick side note here, remember that in physics, the word fluid doesn't just mean liquids like water, it applies to gases too. This upward push is the exact same reason a light bulb will violently pop right back up to the surface if you push it to the bottom of a beaker. It's experiencing that buoyant force pushing it up. Section 3, solving for upthrust. Let's actually do the math and calculate that exact upward force. This is where the math becomes incredibly elegant. We can find the exact magnitude of the water's upward push just by looking at the difference in our scale readings. First, we identify our real weight. That was 10 kilograms in the air. Next, we note our apparent weight, 6 kilograms in the water. Finally, it's just a simple subtraction. We subtract the apparent weight from the real weight. 10 minus 6 gives us our answer, 4, meaning the water in the tub is exerting exactly 4 kilograms of upward force, or upthrust, on our object.
I really want to emphasize this statement to make it stick in your mind. The loss in weight you're seeing on the scale is exactly equal to the upward force the water is applying to the object. They are literally one and the same.
Moving on to Section 4, Archimedes' Principle explained. Now that we know the how, we need to understand the fundamental rule that explains the why.
Enter Archimedes' Principle. This principle lays out two incredibly important points. The first one we've already witnessed firsthand. When an object is immersed in a fluid, it experiences an upward force. The water pushes back. Simple enough, right? But the second point, this is the real genius of Archimedes. It states that this upward force is exactly equal to the weight of the fluid that is displaced, meaning pushed out of the way, by the object.
Section 5, calculating displaced fluid. Let's try out a second practice problem and see how this brilliant second point builds on our math. Let's apply our formula to a new object, say a heavy golf ball. First, we hang the golf ball from our spring balance in the air, and its real weight is 3 kilograms. Next, we partially immerse the ball in a water tub, and the apparent weight on the scale drops down to 2 kilograms. Finally, doing our simple subtraction of real weight minus apparent weight, 3 minus 2, tells us the upthrust is exactly 1 kilogram of force. But let's take this experiment one step further to really test Archimedes' second point. Imagine we place the golf ball into a beaker that is filled to the absolute brim with water. As the ball goes in, it obviously pushes some water out of the way, right? If we collect every single drop of that displaced water that spills out into a separate flask, what do you think the reading will be if we put that spilled water on a weighing balance? It's going to be exactly 1 kilogram.
And honestly, this just brilliantly illustrates the magic of physics. The 1 kilogram of upthrust that we mathematically calculated by looking at the weight loss perfectly matches the 1 kilogram weight of the displaced water. Archimedes was 100% right. The magnitude of the buoyant force is literally always equal to the weight of the displaced fluid. Section 6. Rapid-fire practice problems. Let's run through a few quick rapid-fire applications to firmly cement this concept. Because this rule we just proved, it's completely universal. Let's say you take a radio, you dunk it into a beaker, and it displaces 2 kilograms of water. What's the upward force on that radio? 2 kilograms of force. Now, what if you take a much larger object, like a heavy TV, and you put it into a massive beaker of water? If that TV displaces 10 kilograms of water, you guessed it, 10 kilograms of upward force. No matter what the object is, the upthrust always exactly equals the weight of the fluid pushed aside. Which leaves us with a really fascinating final question to ponder as we wrap up this explainer. We now know for a fact that the upward force always equals the weight of the displaced fluid. So, what happens if an object is shaped in such a way that it displaces more water weight than the actual weight of the object itself? How do you think this mathematical rule applies to giant, incredibly heavy steel ships floating effortlessly on the ocean? Keep that in mind the next time you see a massive vessel on the water. It is all just a grand, real-world application of the simple math we walked through today. Thanks so much for exploring Archimedes Principle with me.